a textile engineer from the University of New South Wales in Australia. She's currently a postdoctoral fellow at the University in Leuven, Belgium, in the Department of Materials Engineering. Her research interests in the design and manufacture of composite parts by concurrent engineering of textile preforms and composite processes.
Good afternoon, ladies and gentlemen. I'm in a very lucky situation because I think I'm one of the only speakers here that can wave around some samples. What I'll be talking about today is composite materials, which I've got an example of. These are the materials that are made from preforms, the glass and carbon fibre preforms. And I'll be specifically talking about sandwich structures, which are made from velvet work and preforms. But let me just give you a bit of background on composites to start with. Composites are a combination of fibre and a matrix system or a resin system. The choice of fibre and the choice of resin system will determine the properties of the final composite. There's an example of some fibre systems on the right-hand side of the screen. On the left-hand side of the screen, sorry. And I'll just point out on the right-hand side of the screen, there's a picture of a composite material that's been taken in a CT scan. And if you have a look at the arrows, they actually point to fibre bundles. So these are actually filaments of glass inside a matrix material. The matrix material is the darker part of the material. Now the properties of these really are highly dependent on the textile structure that's on the inside of the material. So for example, if you have a chop strand mat, you can go from fibre, you can use fibre bundles, or you can use more organised fibres in the form of textile, for example woven and knitted materials. Each of these give you different properties. So for example, if we look at the E modulus at different directions, on the x-axis is the E modulus in the weft direction, and on the y-axis is the E modulus in the y direction. Now for example, the small random fibre mat will give you the same properties in each direction, but those properties aren't particularly good. However, these materials are more formable and quite inexpensive relative to other preformed materials. On the other hand, if you take note of the woven material, the 2D weave, it has very high E modulus along the weft direction and very high E modulus along the warp direction, but in the bias direction, where we all know it can form quite easily, the E modulus isn't so good. But we can use these properties in a final composite to engineer the properties of the composite. This is an example of some 2D materials that are actually made, that are used in composite materials. And the choice of material depends on the shape of the final product that you're looking for. So for example, warp and weft knit materials are used more for formable components where you want to make curved shapes. Something that's more isotropic rather than anisotropic materials, where the properties of the material are the same in each direction. There has been some movements towards making more isotropic materials in weaving. So for example, triaxial weaves and the development in quartaxial weaving in Italy are interesting examples of multi-axial weaving where we're aiming for more isotropic properties. The same with braided, we've got a whole huge range of materials that are possible. All of these 2D materials, or 2D because they're single layer, are usually made up into a composite material by laminating a whole range of the materials together. One of the problems with composites, one of the design criteria for composites is delamination, which means that the layers actually come apart. Some of the weaving development work has been in recent years to look at three-dimensional woven parts. The main reason for this is for delamination properties so that these parts have through thickness strength. But another aspect is so that we can lay the material or fibre down in the direction that we need it, and also have a net shape preform, or a preform that's very close to the final shape of the product, so that it's less expensive to lay up. Of our particular area of research, and there are thousands of examples of different preform types in this field, our area of research at the moment is in sandwich structures, which is on the bottom right-hand side of the screen. Classic sandwich material are made up of a core with two skins that are attached to it. Traditionally, foam and wood cores have been used, and more recently, in the last 30 years, honeycomb and corrugated cores are used. The applications for these are in aircraft, boats. There's thousands of applications. Even the doors that we walk through each day are actually classical sandwich materials. The main problem with these, as I said before, is delamination. So it's actually the surfaces coming off the core material. And our solution was to use integral double layer fabrics, distance knits and distance weaves, to try and make these properties a little bit better through thickness strength. This is a schematic of the weaving method that's used to make these materials, and it should be familiar to most people here. It's actually a traditional velvet weaving process, and for the last, since 1985 in the Catholic University of KULeuven, these materials have been developed. I can pass these around if you're interested in seeing. The pile fibres actually form the core of the final product, and the skin fibres form the skin. So normally in a distance material like this, for traditional textile use, you'd normally cut this layer so that you get a nice velvet surface. So this material is usually produced in two layers at once, just like the diagram shows, but there's a cutting step. And we don't use the cutting step. What we do to manufacture these into this product, and this is actually the preform that's used to make this product, we have a couple of process paths that are possible. The first one is that we can just pour a liquid resin over the preform and roll it in like with a paintbrush roller or a paint roller. And what happens is that the resin goes into the pile yarns and they become quite stiff. So the layers of the two pieces of fabric, instead of being compressed together, actually separate to form a sandwich pile. This method is extremely good for piles that are fairly low height, so up to about 18 millimetres, 16 to 18 millimetres is okay. But anything above that, we really needed a new method to have a look at how to make them in a reasonable way. The other problem with doing hand layout is that we can't control the amount of stretch that we get. We can't control this height very well. And also it's very difficult to control the fibre orientation in each direction between the panel layers. So a new method was developed by Metalito, and essentially this method involves putting the preform with some resin in between two hot plates. The resin starts to melt, and after a few moments it starts to gel at the surface, which is what that means is that it starts to go very sticky on the surfaces. Because it goes sticky where it's the hottest, we can use this to stick the two surfaces to the plates, to the hot plate, and begin to separate the material. And the process window for this is that we need to start separating the material just when the resin becomes sticky on the surfaces. If we leave it too long, then the resin will go hard in the middle, which means that our preform will be stuck and will be a single layer, not a separated layer. After some amount of time, we can then continue to stretch it and to reorient the piles by moving the bottom plate relative to the top plate. So the properties of these materials are different in the warp and the weft direction. So looking at the warp direction, there are three main properties that we can change, or three main parameters that we can look at. Firstly, we can look at the degree of stretching of these materials. If you look at the low degree of stretch, what happens in the warp direction is that a typical figure-8 pile is produced. If the degree of stretch is quite low, we get a resin area that joins one pile to the next. So our core properties, or the shear properties in the core, which means that the bending properties of the core. So this property in here is a lot better if the degree of stretching is low. The other thing that can affect the pile, the core, is the density of the pile, and that's extremely flexible. It just the trade-off is that you get a much heavier hammer if you've got a denser pile. And the other way to control the core shear properties is to actually look at the pile orientation. And to get the ±45 pile orientation in the warp direction is very simple. You simply float the warp yarn, the pile yarn, in the middle of the two layers for a number of weeks before you integrate them into the other layer. In the weft direction, it's a completely different story. The degree of stretching and the pile density really don't have a significant effect in the weft direction. So the only thing that we're left with is to try and reorient the pile. Now there's a schematic of the velvet weaving, and you see the reed in here. Now this reed, as most of you have seen, beats the yarn into the fell of the material, and the movement of that means that all of the pile is oriented along the warp direction. So getting something that's oriented across the loom is technically quite difficult. We looked at a few different alternatives for this, and one of them was to look at reorienting part of the existing structure. And we're looking at reorienting the warp yarns, the pile warp yarns, using some traditional methods that are used for other applications. So for example, in metal dupe lino weaving, we tried using a metal loop that was in the bottom layer. You can see the metal dupe positioned in the bottom layer on the left-hand side. And then if you lift one side of the dupe, the left-hand side of the dupe, you get a left shift of the pile in the upper layer. If you lift the right-hand side of the dupe, then you get a right shift of the pile. And the resulting structure in the weft direction would look something like the pile structure that's down here. And that can be useful for us, but we'd really prefer to have ±45 at the same position. So we came up with a warp crossing method that was initially used for net weaving in the 1830s. But we applied it to distance materials. So now we've got pile in the lower layer, and on the far outer edges of the lower layer are two pile yarns, and they're connected by string dupes. And this is the dupes in the upper layer, showing in the middle ±45 degree pile crossing. Now, actually implementing this on the loom is technically a little bit difficult because all the yarns get in the way and the density of the yarns is quite high. So we proposed a method where we control somehow the amount of movement of each of these dupes using a series of rings. This is the proposed method. I hope you can see that, but that's actually the setup on the weaving loom that we actually wove. And looking back from the reed into the fell, this is the resulting fabric. You can see the orthogonal pile yarns, or the pile yarns that go straight up, which is the normal pile yarn, and you can also see the ±45 pile yarn resulting from this method. The upper skin is formed by the upper warp layer, and the lower skin is formed by the lower warp layer, with the core being formed by the pile. These materials were made up into a couple of panels, and I've got examples of them here, and they were tested for the core shear modulus and strength using a 3-point bend test. We compared the orthogonal pile, which is on the left-hand side, with a ±45 degree warp and weft pile. And we found actually that the ±45 degree method was extremely good compared to the material properties without this ±45 in the weft direction. For future work, if you have a look at the samples, you'll see that they're actually really initial work, beginning of the work. So what we're expecting is that we'll maybe not necessarily need so much ±45 degree weft, because if you have a look at the results of the core shear strength, or the core shear modulus is much, much higher in the weft than the warp, so we might not need to have ±45 so so much crossing in it. So it might be possible to position the crossing mechanism behind the reed and use traditional lino methods as opposed to positioning it in front of the reed. One of the trade-offs is, of course, yarn abrasion. So we're still investigating this area. This work was done on a hand-built loom that we built as part of a PhD program. And now we're looking at getting this work into a production loom. So what we have to do is look at whether or not we can use other existing applications to provide water crossing. The problem is that the number and the complexity of the parameters increases every time you increase the architecture of the pile. There's obviously changes to the timing and all of that sort of thing that we have to do anyway, and compensating for the path length of each of these. So every time you make a design change, you have to incorporate that into the loom. That's normal, I think, for every textile process. So what we've found is that plus or minus 45 degree weft was in fact possible. We have made it, and now we're looking at, it does provide improved core shear properties, and now we're looking at optimising the process. Thank you.
Are there any questions for the speaker?
Excuse me, what for we are using this fabric?
The fabric's normally used in boats. We can combine this type of fabric with phenolic resins and get very good fire-resistant properties, and also when there's a fire it doesn't burn and give toxic fumes. So it's boat applications, flooring applications in aircraft, containment materials for bomb containers in aircraft.
Can be used for isolation for the walls?
Absolutely, yeah, the insulation is excellent. You can also fill the inside to provide cooling. Yes, of course. They can be hollow or foam filled. There's a huge range of possibilities. And they're actually used in double wall tanks, lighting for lining tanks. So underground tanks, petrol tanks for example, need now to be 2 layers. So if we put this material and line the tank with it, then because there's a separation between the inside and the outside, even for old steel tanks, then we can put detection devices, leak detection devices on the inside and detect leaks. So that's the main application. Another application for these materials is to put them onto quite thin layers, is to apply them to a concrete structure.
Isolation for the cables,
as well, yeah, and cables as well.
Thank you.
Any additional questions? Well, delegates, I thank you for your kind attention. This concludes our parallel session today. You'll join me in thanking the speakers once more. And we're finishing just a little bit early, so I